find our mechanical input is this much, electrical output is this much. So here machine will deaccelerate, and due to the deacceleration the angle will again reduce. Okay, angle will again reduce. So it will follow like this, this way, this way, this way, this way. It will be at the stable condition. Again at this point the mechanical will become electrical and it will operate at suppose delta 1, new angle delta 1. Okay, so this is the stable equal criteria. Now if you see the equation, this is further one is there where if you take some angle, suppose, okay, are you seeing the line, skyline? If you take there some angle, okay, suppose this is delta 1, okay, this angle, okay, this is suppose delta 1, this is delta 0, and this is delta. Now what will be the splitted integration? What we can write, this one will go for from delta 0 to delta 1. This equation will split. Okay, this equation will split. Have you taken the photo?
Wait, let me open my camera.
Okay, you will take that one also. So if, okay, let me draw it there now. If I take this one in paint, I think it would be better. See, someone network is not working. Okay, so see this one. Let's take this one as so. Okay, let's take this angle as delta 1. Now from delta 0 to delta 1 machine was accelerating. From delta 1 to delta, electrical power is more, means machine should deaccelerate. So we can split the equation. We can split the equation where equality criteria is here. Which screen is visible now? This screen is visible, huh? Okay. Now here see, all rings. Now we have PA. PA is equals to, sorry, integration of delta 0 to delta is equals to 0. Now this equation can be written as or delta 0 to delta 1 PA. Others are there. PA plus, sorry, PA dt was, the delta was there, d delta. So PA d delta. So this PA d delta is equals to, sorry, Control Z, plus integration delta 1 to delta PA d d delta is equals to 0. So can you write it? Just see the equation. This delta 1 lies in between delta 1 lies in between delta 2 delta 0. Okay. So delta 1 is the angle where delta 1 is the angle where these two are crossing. Okay. So this angle is delta, this angle. Okay. This angle is delta 1. So delta 0 to delta 1 and delta 1 to delta. Okay. Delta 1 to delta. Now if you see this, so we can write this equation. PA delta 0 to delta 1, then delta 1 to delta. So ultimately we will get this. So this equals to 0. Now at this one, delta 0 to delta 1, if you see the diagram, delta 0 to delta 1 till this, machine is accelerating. So this one we can take it as accelerating energy, or accelerating area A1, and integration, because integration represents the area. So from delta 1 to delta, this one we can take it as A2, which is the deaccelerating area. How deaccelerating? Because if you see the equation, to see this equation, that equation again we can write it as this term. This term is suppose our A1, A1, and this term, the whole term is A2. Okay. So what we can write, A1 is equals to, can you write it? Just see, A1 is equals to minus of A2, minus of A2. Yes, can you write it?
Yes, ma'am.
Okay, A1 equals to minus A2. So A1 was accelerating area, which was delta 0 to delta 1 angle, in which, and A2 was deaccelerating area. The angle was from operating at delta 1 to delta. So this is the actually equal area criteria equation. A1 is equals to, means the area A1 is equals to area A2. Accelerating area is equals to negative of this deaccelerating area. So that is the equal area criteria. Now there is something written. The area A1 represents the kinetic energy stored by the rotor during acceleration. Already I told you. And the A2 is the represent the kinetic energy given up by the rotor to the system. Given up. Why given up? Because A2 is minus of A1. Means A1 is the accelerating. This is the deaccelerating. That's why given up by the rotor to the system. Previously it was storing. Now it is releasing during A2. So when all is given up, the machine has returned to its original position. Means, as I said, from the curve, when they are equal, A1 is equals to A2, means, and machine comes here, the electrical power output. At this time, all the energy is given out now. So machine will be in return to its original position. Because why original speed? Because due to acceleration, speed will be more. So when deacceleration starts, then speed will reduce gradually. So the area under PA curve should be 0. That already I told you. When a whole one should be equals to 0. That already written in that equation. Area under this curve PA. This whole term represents the area. Okay. So for stable operation, A1 should be is equals to A2. Actually, this should be A2, huh? This should be A2. So hence the name is equal area criteria, as the areas are equal. Now there are some examples of this transient stability, means why transients creates because of the sudden load change, because of the line outages, and because of the sudden fault. If line, suppose if there is heavy load change means load has been increased to a high value. That time what happens, the machine should supply that load, and for supplying that load electrical power output should be more and machine speed changes, and due to that transient may take place. Then here switching off one line means, suppose there are three lines, power is flowing through three lines. Now one line is not there, so remaining power will be distributed or diverted through the other two lines. So other two lines will be heavily loaded. So heavily loaded means ultimately, if they exceed the limit, the what does it call, exceeds the limit, that line also may get out from the system. Similarly, sudden fault, already you know, if fault happens, the power becomes reduced, and if power reduce, electrical power output reduce means what happens, the mechanical power is constant, so machine will accelerate, means it will run at very high speed. Okay, so these are the examples, some examples of transients in the power system. Okay, so till this, should I explain it from the beginning again? Yes,
Which
tell me.
one? Equal.
Should I explain it from the beginning again? Just let me give you an overview of this again. We do not use swing equation because it is a time-consuming method, and it's a numerical technique. It uses numerical technique. That's why we do not use swing equation for finding out the transient stability of the system. We use equal area criteria. Now equal area criteria is the graphical method for determining the stability and stability limit. Now what is stability limit? Stability limit is the one where maximum power can be transmitted through the line. It is the limit actually, that limit, the maximum power can be transmitted through the line without any outages. So that if we, without any outages, power is transferred, then the maximum power is transferred, that time it is called stability. Now why how this equal area criteria equation is derived, we have taken swing equation. From the swing equation, some methods, sorry, some simplifications are done by multiplying and taking the integration. All these steps are written here. If you go through it, that will be clear to you. Now ultimately we will get d delta dt equals to this equation, where before disturbances d delta is dt is 0, because there is no change in delta, that's why this is 0. Similarly, after disturbance also d delta dt is 0, because there is no change in delta if transient stability is maintained. Then so that's why this the delta dt is equals to 0 is taken in the above equation, and after simplifying we have this equation. So as this is the integration of this power, this represents the area, and we have split it in two area. One is accelerating area, another is the accelerating area. So that already I have showed you in this whiteboard. Accelerating area, deaccelerating area. Accelerating area is negative of the deaccelerating area, as these two areas are, when these two areas are equal, means equal area criteria is achieved and system will be stable if they are equal. If they are not equal, suppose A1, suppose A1 is more than the A2, then stability will not be achieved. A machine will not run it at synchronous speed. So stability will not be achieved if A1 is greater than A2. So that things are written here actually. This term should be A2. Okay, so that's all. and you all these things are written. Please go through it, then only you can understand. Okay.
Okay, ma'am, syllabus will be.
Oh, syllabus for that, syllabus for this class test. Syllabus will be your this, what does it call? First of all, we have done load flow, na? Load flow analysis. Load flow analysis will be there, and power system faults will be there, and the self study part, whatever I have given, like economic choice of conductor size, that Kelvin's law, and next, what is that? Yes, effect of system voltage. Effects of system voltage on transmission, like three effects are there. One is volume of the conductor, and another is transmission efficiency, and another is uh, percentage line drop. If we transmit power at high voltage, what will happen? The volume of the conductor will be reduced, and secondly, transmission
This one will come
efficiency.
over this one Newton-Raphson method.
Newton-Raphson method is required.
Mm.
Newton-Raphson method is required. So you go through it. If you have any doubt, you can ask me at any time. You can call me also. If you have doubt, please go through the materials, whatever I have shared from the BK Mehta book. You have to study something. No, I have shared already. So that things you do. If you have doubt, to ask. Okay. So thank you for coming, and you go through it. Okay, I will share this. Okay. Bye bye.
Mm.